Right. So, good afternoon. Welcome to the second tutorial sessions on ME67 wheel mobile robots. So, since this has been our second week, I hope the all of your courses are actually going pretty well. So, in the last class, it was more or less preliminary discussions on different kinds of robotic systems. We actually began with the manipulators. We discussed about the distinction between robotic manipulators and mobile robots. We have also covered the different kinds of mobile robots that are available, whether it is land-based mobile robots, be it underwater robots, aerial robots, or so mobile land-based mobile robots actually. And then we have actually narrowed it down all the way to wheel mobile robots, and we have also discussed various subsystems of wheel mobile robots. And from week two onwards, this is where we actually cover the mechanics of wheel mobile robots. So starting with kinematics. So like I hope you have gone through all the lecture videos regarding week two, but we'll basically cover a summary of a few important topics such as how the generalized wheel model is derived and how it can be adapted for various wheel mobile robot configurations. And further, we'll also solve some tutorial problems that will get you to practice so that you can easily solve the quizzes or the assignment questions. So, without delaying in anything anymore, any further, we'll get on with the topics for this tutorial session. So we'll basically review how to derive the generalized wheel kinematic model. So if you have gone through the lecture videos, you might have come across various kinds of wheel mobile robotic configurations, such as what do we have? We have differential drive, I suppose. I hope you can remember all these different names that I'm putting here. Differential drive. We also have covered the skid steering configuration. Then we have also covered omnidirectional wheels using a mobile robot configuration using three omnidirectional wheels. Wheels. Then we have also covered a holonomic robot with four mechanism wheels. Mechanism wheels. And further, we have also covered mobile robotic devices which can also have a steering axis. So something like a tricycle mobile robot, tricycle like, where the tricycle like robot will have powered wheels as well as steerable wheels. And all the four previous configurations that I have written here, they only have driven wheels. They don't have a dedicated steering axis. But over here, what I've named here, the tricycle-like kind of a configuration, will also have steerable axis. Same in the case of SWERV drive, SWERVE, DRIVE. So this configuration will also have drivable and steerable wheels. So like in order for us to cover the kinematics of all these sort of mobile robotic configuration, it would be very convenient to have a generalized wheel model. So if you have a generalized wheel model, you can easily adapt a generalized wheel model for any of these different configurations of wheel mobile robots. Right? So that is why we call it a generalized robotic configuration. So derivation of a generalized wheel configuration or a generalized wheel robot consists of, for example, like we have basically defined here a frame that is fixed on the robot's chassis. So this frame, we'll label it as the frame B. It will move with the robot. It will move with the chassis of the mobile robot, whatever be its position and orientation. We also have an inertial frame of reference that will be always fixed with respect to the ground. So that won't move anywhere. And we also have one more frame of reference over here attached at the wheel. So depending on whether the wheels are steerable or whether the wheel is steerable or is it fixed, the orientation of this frame C will also change, right? So each wheels will also have their own local wheel axis. So we have labeled it here as XCI and YCI, which are the coordinates. So in order for us to track the orientation of each of these frames, we'll label the orientation of the frame V with respect to frame I with a variable called as psi, which is in tune with what we have covered in the lectures. And the orientation of the x-axis of frame C with respect to the body frame, x-axis of the body frame, we'll call it as theta B. Let this be theta B I. So I can be for I basically denotes the wheel number. It could be 1 for wheel number 1, 2 for wheel number 2, so and so. So what are the parameters that we have? We basically have a wheel that is driven by a motor. So we have the driven velocity of the wheel as this component over here. We'll call it as V drive. So this V drive is basically fully contributed by the driven motor or the mobility of that particular wheel. And we all, since the wheel has passive rollers, so since this is generalized wheel model, we also have passive rollers over here. So depending on the configuration of the mobile robot, we can adopt the passive rollers. We can simply omit the passive rollers, or if we wish to have non-conventional wheels to our robot, we can basically have the passive rollers. So if that is the case, we have a sliding velocity along this direction. We'll call this as V slide, right? So if omega I is the angular velocity of the wheel, the primary angular velocity of the wheel, and if AI is the radius of the wheel, then V slide would be omega I AI. This would be nothing but V slide, right? And in the case of, sorry, this will be V drive, actually, V drive, right? And if rho I is the radius of the rollers, the passive rollers over here, right? And beta I dot is the rate of rotation of the passive rollers, then rho I beta I dot would be V slide, right? I hope that is clear. And we are only using omega I, which is driven by the motor, to drive this entire wheel. Whatever we have over V slide is basically passive, because the passive rollers are not actuated. Only the main rollers or the main wheels are actuated. So if we resolve everything along XCI and YCI direction, so we want to resolve this V slide and V drive along these two axes, XCI and YCI. So how do we do that? So the velocity along XCI, I'll call this as XCI dot, will be V drive is fully along XCI. So it'll be omega I AI, and the component of V slide along XCI axis, right? That would be minus rho I beta I dot sine phi I. So I'll label this as equation 1. So I have forgotten to rename this label one important parameter. This is basically the angle phi. So this phi is basically nothing but the angle the V slide makes with YCI axis, right? So if this is YCI and V slide is along this direction, the angle between V slide and YCI is considered to be phi. So resolving V slide along XCI axis would be, it will be this component actually. So that will be V slide sine phi I. And resolving everything along YCI axis, the resultant velocity would be sorry, I'll use the same color for consistency. YCI dot would be, so there will be no component of V drive along YCI because V drive is fully along XCI. There will be no component along YCI. So the only component of YCI velocity would be V slide cos phi. That will be this component. So that will be rho I beta I dot cos phi I. I label this as equation 2. And from 2, I'll simply rewrite rho I beta I dot as YCI dot by cos phi. So I label this as equation 3. So substituting equation 3 into 1. So 3 in 1 would yield XCI dot would be omega I AI minus, instead of rho I bi, I'm writing this as YCI dot by cos phi I. So YCI dot by cos phi I sin phi I. So I label this as equation 4. Or you can rewrite this in a different form. You can write omega I as 1 by AI as a vector of XCI dot YCI dot. So this will be nothing but 1 by AI and phi I by AI. So I hope this equation is clear. I'm only rewriting equation 4 in this form. Right? So I label this as equation 5. Right? So this XCI and YCI, they are all expressed with respect to frame C. So it may be confusing at the beginning, but the vectors XCI and YCI are all represented with respect to the frame CI. This is the frame CI. So I'll write a superscript over here, CI, to denote that all the quantities derived in equation 5, they are all represented with respect to frame CI. And you can actually bring everything back. You can represent XCI and YCI with respect to frame B, right? The vectors XCI and YCI with respect to frame B. How do we do that? So you can do that simply by using a rotation matrix that basically maps the rotation of frame C with respect to orientation of frame B. So in order for to do that, it will be a simple transformation of XCI, YCI represented with respect to frame B is nothing but cos theta bi minus sin theta bi sin theta bi cos theta bi. This multiplied by XCI dot YCI dot represented with respect to frame C. Okay. And this is exactly the term that we have over here. XCI represented with respect to frame C and YCI represented with respect to frame C is the term here, this vector, on equation 5. Then we can substitute XBI dot XCI with respect to frame B and YCI with respect to frame B onto this equation. How do we do that? So if you multiply this, if you take the inverse of this transformation matrix, this rotation matrix, and re-multiply with respect to this vector, we'll get this vector. So substituting that, we can easily bring everything in terms of the body frame B. So how to do that? So like what will be the inverse of this matrix? Right? This is an orthogonal or an orthonormal vector. This is nothing but a rotation matrix. So if you want to invert this matrix, since this is an orthonormal matrix, the inverse would simply be the transpose. Right? So if I transpose this and pre-multiply this, what will we have? So cos theta bi sin theta bi minus sin theta bi cos theta bi multiplied by xci dot yci dot. These are all represented with respect to b, and this will be nothing but xci dot yci dot in frame C. So this will be equation 7, right? So if I back substitute equation 7 onto equation 5, right? So 7 in 5 will yield omega I as 1 by AI, 1 by AI times tan phi I. Then we also have cos theta bi sin theta bi minus sin theta bi cos theta bi multiplied by xci yci dot, everything represented with respect to frame B. So I'll call this as equation 8, right? So we have basically mapped omega I, the angular velocity of the wheel, all the way to xci represented with respect to frame B, right? And we also know that the velocity of the mobile robot will be mostly represented with respect to its local frame. So if you recall the previous week's lectures, we have the notations that we use for representing the instantaneous velocity of a mobile robot represented with its own frame of reference is u meters per second or u units per second along xb axis, and along yb axis it will be v. The linear velocity, instantaneous linear velocity would be v, and about the zb axis, the instantaneous rotation would be an angular velocity r. Right? If the mobile robot's base have velocities u, v, and r, then what will be the velocity of this point xci? Right? So that is nothing but, if you if you consider the frame of the velocity of the body frame to be uv and r, so if that is the case, then xci dot represented with respect to v would be u minus r dy I. So I'll give this as equation 9, because u would be the linear velocity component along xb would be u, right? And since there is also an angular velocity component, there will be a linear velocity component due to this angular velocity. That would be nothing but omega cross r. So if this distance, if I label this distance as dy I, and this distance, the x and y coordinates of the center of C frame with respect to B frame would be dxi and dyi, right? So the velocity of the point C would be u, plus there will be also a component of this angular velocity. So that component would be along this direction, right? That will be dy multiplied by angular velocity r. So that will be along this component, because r is considered positive along positive z axis. So that will be a counterclockwise angular velocity. So the resultant would be u minus r dy. So that is what I have written over here. Then what about the y component? Y component would be v plus there will be another component due to this display, due to this offset dxi multiplied by angular velocity r. So that will be along this direction. So both of them could be added. So the total linear velocity along yi direction would be v plus this component, that is nothing but r dx. Angular velocity times this distance dx. So if that is the case, then v yci dot puv v plus r dx I. So I'll call this as equation 10. So I can also write equation 9 and 10 in vector form. So xci dot yci dot represented with respect to b frame. We have to map this with u, v, and r. So what will be the mapping that maps xci dot yci dot to uver? So if you consider these two equations, 9 and 10, that will be nothing but 1, 0 minus dy, and the second equation would be 0, 1 dxi. So I'll call this as equation 11. Right? If you substitute this vector onto equation 8 over here, right? So you have to post multiply these two vectors over here. You have to replace this vector by these two vectors. So as a result, you will get this big expression, which is nothing but the generalized wheel model of a single wheel, right? So it will be basically a multiplication of four matrices, this one, this one, this one, and this one. So this is nothing but a mapping between the control inputs of the body frame, u, v, r, and the angular velocity of the wheel. So this is nothing but the generalized wheel model, and depending on the kind of wheel, whether it is steerable, whether it is fixed, whether it has passive rollers, and also the location of the wheel, you can basically have the parameters within this generalized wheel model basically changes. So again, this is also yes. So this is also an advantage of having a generalized wheel model. So depending on the kind of wheel that you have, you can actually adapt this generalized wheel model so that it will suit to your purpose, right? So we'll go on with a few examples. So over here, we have a configuration called differential drive. EIFF. Yeah, also I've written it over here. So yes. So this configuration is called differential drive. So it has a robot chassis and two driven wheels, two fixed but driven wheels are attached at either sides of the chassis. So this is, we'll label it as wheel 1 and we'll label this as wheel 2. So again, like as you know, we have 3 degrees of freedom. The wheel mobile robot can rotate along 3 directions in a plane, that is translations along 2 directions parallel to the plane, and rotation about an axis perpendicular to the plane. But here we have only two control inputs to drive wheel 1 and to drive wheel 2. Right? So if that is the case, then how do we adapt this generalized wheel model? Right? So for wheel 1, so like I here can be for 1 and 2. So here this I term denotes the wheel. So here, since we have only two wheels, we have I equal to 1 and 2. So like what are these parameters for the differential drive? So In this case, A is nothing but the radius of the wheels. So A1 and A2 are basically the same because we have the same diameters. And phi 1 and phi 2 are basically the angle the roller makes, the sliding velocity of the roller makes with respect to the YCI axis, like as we have seen in the previous video, previous slide. So if this is the roller axis, sorry, if this is the sliding velocity of the roller, and if this is the YCI axis, right, the angle between the V slide and YCI is phi. So here, since we don't have any passive rollers, phi 1 and phi 2 can be considered to be 0. And yeah, theta bi is how the wheels are oriented with respect to XBI, XB and YB axis. So here essentially the steering axis or the wheel axis is always going to be remain fixed. So in this case, our YCI will be like this, or rather YC1, and XC1 would be like this. And since there is no apparent orientational difference between the C1 axis and the B axis, theta B1 is essentially 0, and the same goes for theta B2. So theta B1 and theta B2 are also 0. And what about these terms dYIA and dXi? So dy1 would be this distance from the B frame to the C frame. So here this entire width of the chassis is given as 2d. So dy1 would be d, and dy2 would be minus d. And since the x-axis of the frames, both frames, C1 and C2 coincides with XB frame, dx1 and dx2 are 0. Right? So if you plug in all these parameters onto the generalized wheel model, you will get an expression something like omega 1 would be 1 by a 0, then 1 0 0 1, 1 0 minus d 0 1 0 UVR. So this entire thing can be clubbed together and be written as 1 by a 0 minus d by a UVR. This is omega 1. And similarly, omega 2 can also be written as 1 by a 0 d by a UVR. So you can basically write everything as a vector matrix form. Omega 1 and omega 2 can be written as a vector. UVR also can be written as a vector. So as a result, it'll be something like this. Omega 1, omega 2, it should be mapped to UVR. So how do we do that? So that will be 1 by a 0 minus d by a, 1 by a 0, then v by a. So in this case, the real problem would be if we require a desired UVR, then how would you calculate omega 1 and omega 2? So if you know this matrix, you only need to pre-multiply UVR, the desired UVR with respect to this matrix, so that you will be able to get the angular velocity of each of these fields. But as you can see, this is also a non-square matrix, right? This is a 2 cross 3 matrix. So if you want to take this inverse, if you want to find UVR for a given omega 1 and omega 2, you will have to pre-multiply this side, the left-hand side, with an inverse, some sort of an inverse of this matrix. But as this is non-square matrix, you will have to take something called a pseudo inverse, right? So depending on the kind of system, if depending on the kind of linear system that you have, there are different kinds of pseudo inverses that you have to take. It could be a left pseudo inverse, or it could be a right pseudo inverse. We'll look into that when on subsequent slides. But if you have a system, if you have something like MATLAB or anything, there is a command called P inverse. So if you want to take an inverse of a non-square matrix, you only need to give this matrix as an argument inside this PINV command. So it'll automatically take care of the left inverse or right inverse. You don't have to explicitly specify which inverse to take. So if you do that, once you take the pseudo inverse, you can basically write it as, yeah, I'll erase this and I'll write this final expression. So it'll be U V R would be A by 2, 0, 0, minus A by 2D, omega 1, omega 2. And this is basically the kinematics of a differential wheeled robot. And what you have over here is called a wheel configuration matrix, right? So this can be written in a compact form as zeta is W, capital W times this vector omega. The vector zeta is the matrix W multiplied by the vector omega, where the matrix zeta is UVR, the instantaneous velocity coordinates of the body frame, and omega 1, omega 2 are the angular velocities of the wheel. And this matrix W is nothing but the wheel configuration matrix for differential drive robot. Right? So that is one example. That is how we basically adapt or adopt the generalized wheel model for differential drive. We can also do the same for skid steering drive. So here we can consider this to be wheel 1, this to be wheel 2, this to be wheel 3, this to be wheel 4, and the length of the chassis, length between the wheel axis of the forward and rearward wheels are considered to be 2L, and the width between the front two wheels or the rear two wheels is considered as 2D. So if that is the case, how do you adapt these parameters? So in this case, we have the radius of the wheels A1, A2, A3, and A4 as A, because the wheel radius are all constants. And theta bi is basically the angle between the frame C and frame B. So again, as you observe, the frame C here and frame B here are basically of the same orientation. There is no relative orientation between frame C and frame B. So that can be said for all the four wheel frames. So IC2, XC2 here as well, YC3, XC3, and here YC4, XC4. So theta B1, theta B2 are all 0, theta B1, theta B2, theta B3, theta B4, they're all going to be 0. And what are the remaining terms? We have these terms over here, dyi and dxi. So dy1 would be positive D, dx1 would be positive L, dy2 would be again positive D, dx2 would be negative L, dy3 would be negative D, dx3 would be negative L, dy4 would be negative D, dx4 would be positive L. So for all four wheels, if you substitute all of these parameters onto the generalized wheel model, you will basically end up with four equations. So I'll give the final form of these equations as it'll be something like omega 1 would be 1 by A, 0 minus d by A, UVR. Omega 2 would be again exactly the same, I suppose. 1 by A, 0 minus d by A, UVR. Omega 3 would be 1 by A, 0 d by A, UVR. And omega 4 would be 1 by A, 0 d by A, UVR. So if you club everything together, you can write it as a matrix and vector form. Omega 1, omega 2, omega 3, omega 4 would simply be 1 by A, 0 minus d by A, 1 by A, 0 minus d by A, 1 by A, 0, d by A, 1 by A, 0, d by A, UVR. And if you take the pseudo inverse of this matrix over here, what I have written here, you will get the wheel configuration matrix for the skid steering robot, which is nothing but it'll look like W would be A by 4, 1, 1, 1, 1, then 0, 0, 0, 0, minus 1 by D, minus 1 by D, 1 by D, 1 by D. So what you have over here is the wheel configuration matrix of the skid steering robot. We will also have an A by 4 pre-multiplied over here. So there is a relation. You can basically relate the theta, which is the control input to the wheel, control input to the base, the body fixed frame, with and the vector of angular velocities using this wheel configuration matrix W, right? And similarly, you can also find the wheel configuration matrix for this mechanism wheel drive. So I'll simply give each of these parameters. So here, as per our convention, since the direction of V slide is at an angle phi1 with respect to YC1 axis, so phi1 would be 45, whether it is positive or negative, phi1 would be 45 degrees. And here, in this case, it will be minus 45 because we are rotating along the clockwise direction. So this is 45. Here, this is 45. And here, it will be minus 45. Right? So if that is the case, A1, A2, A3, and A4, they're all the same A. Phi1 is 45. Phi2 is minus 45 degrees. Phi3 is 45. Phi4 is minus 45 degrees. And just like in the previous cases, theta bi, which is the orientation between the wheel frame YC1, XC1, and the body frame YB and XB. So here in this case also, there is no apparent orientation, relative orientation between the wheel frame C and the body frame V. So in this case, theta B1 and theta B2 as well as theta B3 and theta B4 are all going to be 0. And just like in the case of a skid steering robot, we have exactly same dx and dy parameters. dx4, dy4. So dx1 would be L, dy1 would be D, dx2 would be minus L, dy2 would be D, dx3 would be minus L, dy3 would be minus D, dx4 would be L, dy4 would be minus D. So once you substitute everything onto this generalized field model, and if you repeat the process, you will end up with the wheel configuration matrix for the mechanical wheel drive as, yeah, you will get it as A by 4 times 1, 1, 1, 1, 1, minus 1, 1, minus 1, minus 1 by D minus L, minus 1 by D minus L, 1 by D minus L, 1 by D minus L. So using this wheel configuration matrix, you can map the control input vector theta with respect to the vector of angular velocities of the wheel using this wheel configuration matrix over here. So that is also straightforward. And yes, there is also one more wheel that is actually could be interesting as well. What we call this as an omnidirectional drive, three-wheel omnidirectional drive. So in this case, like it's unlike what we have seen because the wheels are all over the place. And I'll again give you the parameters, each of these parameters. The wheel radiuses are still constant. A1, A2, A3 are all A. And theta theta B1, theta B1, theta B2, theta B3. These are not zero anymore because they are changing. They have different orientations compared with what we have seen in the earlier case. So in this case, theta V1 would be the orientation, change of orientation between the frame XCI and, sorry, the frame C1 and the body fixed frame B1. So here I have basically, I think it's an error. So XC1 would be along this direction. So I'll just correct it. So this should be XC1. XC1 is 90 degrees with respect to XB1, XB. And YC1 is basically along this direction. This is YC1. So since there is a 90-degree offset between XC1 and XB, theta B1 would be 90 degrees, right? And what will be theta B2? So there is basically a 120-degree offset between all the coordinates in B frame, all the coordinates in wheel 1, wheel 2, and between wheel 2 and wheel 3. So theta B2 would be 90 degrees plus 120 degree, that would be 210 degrees, and theta B3 would be again a relative angle of 120 degrees, that will be 330 degrees. And what would be dyi and dxi? dx1, dy1, dx2, dy2, dx3, dy3. So dx1 would be the x coordinate, the position of the frames, the position of the frame CI along xb axis. So that is nothing but L over here. That's nothing but L. So dx1 would be L. And dy1, we don't have to translate any units along yb direction because the frame C1 is lying on this xb axis. So dy1 would be 0. And what about dx2? So as you know, x2 is at 120 degrees from xb axis. And the distance between, the radial distance between the center of the B frame and the C2 frame is L. So in that case, dx2 would be L cos 120. And similarly, dy2 would be L sine 120. And using similar reasoning, dy x3 would be L cos 240. dy3 would be L sine 240. And again, just like in the previous case, if you plug in all the parameters, you will get the wheel configuration matrix as 0 minus a root 3 by 3, a root 3 by 3, then 2a by 3, minus a by 3, minus a by 3, then a by 3l, a by 3l, a by 3l. So you can map the vector of input controls with a vector of all the angular velocities of the wheel using this wheel configuration matrix. So like we have seen different cases of mobile robots here. If you can see, the wheel configuration matrix have one entire row 0 because the total degree of freedom is 3. But if you multiply this out, what will be the component V? What will be this component over here? V. V would be 0 times omega 1 plus 0 times omega V2, right? So at no instant, this configuration can have a velocity along this YCI axis. It has only two inputs, and it cannot have, because as the resistance along the lateral direction is infinity, it cannot have a pure velocity component uh, along the YB frame. And same in the case of this skid steering drive. Here also one full row is entirely of 0. So at no instant can it have a pure velocity along the YB axis. But as opposed to the differential drive, it will have 4 control inputs. So like more control inputs than the degree of freedom, but still it does not give you the maneuverability as when compared with other the holonomic device and the three-wheeled omni drive configuration. So earlier it only had two inputs, but still it cannot move in all directions. Here it has 4 wheels, but still it cannot move in all directions. And here in the case of a mechanowheel drive, all the entries here are non-zero. So it has high degree of maneuverability. It can go forward and backward along x-axis. It can go lateral direction along YB in positive and negative. So by keeping the same orientation, it can go laterally, positive and negative axis. So it can even do, by keeping the same orientation, it can go diagonally along this direction and this direction. It can go along this direction and this direction. And apart from that, it can also rotate about its own axis with 0 turning radius. And same in the case of an omni-wheeled drive, it can go forward and backward. It can go laterally from side to side by keeping the same orientation. It can also rotate about its own axis with 0 turning radius. It can go diagonally by keeping the same orientation. So like all sort of maneuverabilities are available. So like these sort of robots are where it can achieve or where it can realize all sorts of maneuverability are called holonomic robots, uh, where it can also easily be tested. If you check the rank of this W matrix, so which all configurations have a full rank, that is 3, they are all holonomic. So in this case, the rank of this W matrix for omni wheel is always going to be 3. And same in the case of a mechanowheel drive, that is also going to be 3. So like that means it can realize all sort of movements, U, V, R, or any of their combinations. They can realize that. So that's make them autonomous. Whereas in the case of a skid steering robot or a differential drive robot, the rank of the W matrix is never going to be 3. It will be always less than 3. So that means they are non-holonomous, right? So yes, that's what holonomic and non-holonomic systems are about. And we also have seen cases like we have the wheel model as theta as W times W, where theta is UVR and omega is omega 1, omega 2, etc., depending on the number of control inputs that you have. And as you might have observed, the W matrix need not be square all the time. So in the case of a mechanism wheel drive, W matrix is actually, it's 4 cross 3. Sorry, it's 3 cross 4. It's a not square matrix. And in case of, yes, in case of this one, skid steering robot, it's also 3 cross 4, 3 rows and 4 columns. So if that is the case, then you may often need to take the inverse of this W matrix. Right? For example, if you are given this, if you are given all the wheel velocities, and if you want to determine this vector, like how will the chassis of the mobile robot moves, you can simply pre-multiply this with W matrix. But what about the inverse problem? If theta is given, and if you want to find out omega, then you have to pre-multiply this matrix to the left-hand side, right? You have to take the inverse of this matrix and pre-multiply to theta. But since this is a non-square matrix most often, that is going to be different. It's not very straightforward. And that is where we have something called, that is where we take this pseudo inverse actually. So we basically have two kinds of pseudo inverse, one for over-specified systems and one for under-specified systems. So for example, for over-specified systems, I'll give an example. Over-specified system. So zeta would be W times omega. So here, if W is of the order m cross n, and if m is greater than n, so what does this mean? If m is actually greater than n, if UVR, if obviously there is going to be two states, UV and R. So if the number of equations are greater than the number of unknowns, then what is going to happen? You have three equations to satisfy, but you only have two unknowns. So if that is the case, then the solution may not even exist at all. Right? You have three equations, but how can you have three equations to satisfy, but how can you satisfy these three equations using two unknowns? So you may not even get a solution at all if the system is over-specified. So for example, if you have three states, U, V, and R, and you only have two control inputs, maybe omega 1 and omega 2, right? As in the case of a differential drive. So if that is the case, finding an inverse may not be even practical at all. So how do you solve this? So you can only solve this system approximately. So what I mean by approximate is that like you can minimize the least squares. You can basically minimize the square of error between the left-hand side and right-hand side of this equation. So if you consider this as left-hand side, and if you consider this as right-hand side, this is never going to be equal because there may not be even a solution at all. So all you can do is you can basically minimize the least square error between left-hand side and right-hand side. And how do you do that? You do this by minimizing this objective function L. I'll call L as an as objective function. So our objective is to minimize the least square error between the left-hand side and right-hand side. Right? So you have to find an omega such that it minimizes the least square error between the left-hand side and right-hand side of the system of linear equations. So in order for, you can also write this expression as a vector operation. So this is nothing but theta minus W omega transpose theta minus W omega. So if you are still confused, I can simply give you this. The order of this would be 1 cross 3, and this would be 3 cross 1. So then total order would be 1 cross 1. So this is nothing but a scalar that is equivalent to this expression. That is nothing but the least square error. So if you want to find out this omega that minimizes this objective function, all you have to do is you have to take the derivative of this objective function with respect to omega. You have to find out omega where the derivative of L turns to 0. So how would you take the derivative of this expression? So if you take the derivative of this expression, like this is something squared, so a parameter squared, so that will be nothing but this will be minus this will be minus theta minus W omega, the whole transpose. Then we also have a coefficient of omega as W. You will have to multiply with omega. Sorry, W. This will be 0. There should be a 2 also, but since 2 can be taken to the other side, so that becomes 0. And why this negative sign? Because the coefficient of omega over here is minus W. So that is why we have a minus over here, and we also multiply this with W. So if we expand this expression, this will be nothing but, this will be nothing but minus theta, minus theta, sorry, minus theta omega, sorry, again, if you expand this, this will be minus theta transpose minus omega transpose W transpose, the whole multiplied by W. So what I have done here is that, like, if you have AB, the whole transpose, this will be B transpose, A transpose. So that is what I have done here. So this is A and this is B. So this is B transpose, this is A transpose. So if I further expand this out, this will be minus theta transpose W plus omega transpose W transpose W. This will be 0. And rearranging this will be nothing but omega transpose W transpose W is theta transpose W. And your objective is to find out the vector omega that satisfies or that approximately satisfies this equation over here, so that the least square error is minimized. So again, if you take the transpose of this equation, the entire transpose of this equation, how will that turn out to be? So that will be W transpose W omega. This will be W transpose theta. So omega would be, I'm taking this 2 terms to this side. So that will be W transpose W, the whole inverse W transpose theta. And this term, what we call is the left pseudo inverse, right? So the left pseudo inverse W plus is W transpose W the whole inverse W transpose. And we use the left pseudo inverse when the system is overdetermined, right? And the omega that we basically find here is not an exact solution. This is more or less like an approximate solution. Because as I've already said, we cannot have an exact solution if the system is overdetermined. We can have an approximate solution such that the least square error is minimized. So what we have over here, I'll write it a star over here. This is an approximate solution of omega such that the least square error is minimized. And what you have over here is called a left pseudo inverse. And in order for the left pseudo inverse to exist, the regular inverse of this term should exist. So what does that mean? W transpose W whole inverse is nothing but adjoint of W transpose W divided by determinant of W transpose W. So in order for the left pseudo inverse to exist, the determinant of W transpose W should not be zero. So if that is zero, then the left pseudo inverse will not exist. So yeah, if you have a system, if you have an overdetermined system, this is how you solve. This is how you take the pseudo inverse. And similarly, what about the other case? I'll try to be very concise. If you have an underspecified system, So again, if I represent the wheel model, the wheel kinematic model of a mobile robot as theta would be W times omega. So here, the underspecified system would mean the number of variables would be more. The number of control variables would be, yes, much higher than the control input. So if we have M, if the order of the W matrix is M by N, and if M is less than N, we have an underspecified system. So like, what does this mean? Like if we have, theta is always going to be 3 because you have 3 control input vectors, U, V, R. But if omega is actually more than 3, if there are 4 wheels or if there are more than 4 wheels, then obviously the system would be underspecified. So you will only have fewer equations than the number of unknowns. You have more unknowns than the number of equations. So like, what could be the implication of that? You can have multiple solutions. So earlier we may not even have, like if all the systems are dependent, you may not even have any solution. But here, since the number of variables are more than the number of equations, you can have multiple solutions. Then how would you solve this system of equation? How can you solve this thing? Right? So out of this multiple available solutions, which solution would you choose? So what we would mostly follow is we would select a solution that will have a minimal norm. So like, for example, if I consider if omega star is a particular solution, a specific solution to this problem, we choose this omega star such that norm of omega star is minimal compared to all other solutions. So you can think of this as a reason because omega could be considered as how much effort that you are giving onto the actuators. If there are 4 motors, omega would be the omega 1 square plus omega 2 square plus omega 3 square plus omega 4 square, entire thing under a square root. So that will be the norm of this vector omega. And if you have minimal norm means the solution that requires least amount of actuator effort. You could basically interpret it as such. So the solution which requires the least effort from the actuators could be considered as the minimal norm solution. So that is why we mostly stick with minimum norm solution. So how do we formulate this problem? We want to find the solution of this problem such that the norm of omega would be minimal. So here also you will have to formulate an objective function as such. So here the objective function would be L would be omega times omega, right? So that is nothing but minimal now, but squared. It still does not make any difference. It's squared. Instead of taking under root, you are not considering this under root. So omega times omega would be a scalar quantity. That will be simply what? Omega 1 square plus omega 2 square plus omega 3 square and so on. Plus such that you'll also have to satisfy this constraint. Theta minus W omega. So what this objective function means is that you have to find a solution with minimal norm, the solution for omega such that, or minimal norm solution such that it follows these conditions, these constraints actually. So like this is a standard constraint optimization problem. So the constraints are basically this one. This is the constraint omega have to follow. And what you have over here is something called a Lagrange multiplier. So like this is a typical format of a constraint optimization problem. So how do you solve that? So the minimum solution, solution can be considered by taking the derivative of this L, just like how we did in the last time. Dou L by dou omega should be 0, and dou L by dou lambda should also be 0, because lambda is a Lagrange multiplier. That is also another variable. It's just like a weight. How much each of these constraint should be weighed. Like depending on the importance of the constraint, each of these constraint can be given different weights. And since we have two equations, we have to minimize since we have two variables in omega and lambda, we have to minimize this objective function with respect to these two variables. So considering the first equation, I'll label this as equation 1 and equation 2. So dou L by dou omega equals 0 would mean, how would it look like? We'll have 2 omega transpose minus lambda times W. This has to be 0. I'll label this as equation 3. And from the second condition, dou L by dou lambda equal to 0, this would mean, zeta minus W omega. This should be 0 because derivative of this term with respect to lambda would be nothing but this term. So I label this as equation 4. Right? So from equation 3, I'm simply rewriting. This would be nothing but omega transpose is nothing but lambda transpose W by 2. So if I take the transpose of this, okay. With whom you are interacting are not audible. I got a message. Questions asked by other person are not audible. So is that audible for you? So are the questions asked by anyone else audible to any of you guys?
Only your voice is audible, sir. Other person's voice is not audible.
Okay. So I don't know how that is happening. If there are
Okay,
any questions, would it be possible to directly? But I can hear yours actually. I can hear your voice.
maybe you have to ask
Kamala,
the other part. Yeah, Kamalakar. My name is Kamalakar, sir.
look,
Maybe
Kamalakar, I can
other
hear
person.
yours. I can hear yours. I don't know why I cannot hear others actually. But you can hear others' voice
No,
also, right?
I'm able to hear only your voice, sir. I From the discussion, I'm understanding that you are interacting with some other person.
No,
That
actually, no
person
one is. I think they are all listening to my lectures. No one is actually interacting. No one
oh,
else is talking. Actually, yes.
okay, okay. I'm sorry, sir. Okay, I'm sorry.
Okay,
Okay.
no problem, no problem. So if I am simply taking the transpose of this entire equation, you will get omega would be W transpose lambda by 2. I label this as equation 5. And if you substitute equation 5 to equation 4, right? So 5 in 4, this would mean zeta minus W. So instead of omega, I'm writing it as W transpose lambda by 2 is 0. And so from here, what will be lambda? Lambda would be 2 zeta. Sorry, I'll write one more step. Zeta would be W transpose lambda by 2. So in this case, lambda would be 2 zeta. Then, sorry, you will have a zeta, then W transpose the whole inverse. Then you will also have a 2. So I label this as equation 6. So finally, if I substitute everything, where are we now? Yes, if I substitute this equation 6 onto equation 5, how are we going to get? So here omega would be, for I'm rewriting equation 5. I hope you can see equation 5 here, this one. So omega would be uh, W transpose. So instead of lambda here, sorry, instead of lambda here, I'm writing this equation from equation 6, and this 2 and this 2 will get cancelled. So you will end up with W transpose the whole inverse zeta. So where this term is what you call the right pseudo inverse, W transpose W transpose inverse. So this is the right pseudo inverse. So if the system is underspecified, or if the number of equations is less than the number of unknowns, you will have to take the right inverse to solve the system of equations. And the right pseudo inverse will only exist if, just like how we did the last time, W transpose the whole inverse should, if that should exist, then W transpose, determinant of W transpose should not be 0, right? So because this term is adjoint of W transpose by determinant of W transpose. So if determinant of W transpose is 0, this term will not exist. So as a result, this term will not exist. So that is how, yes, that is how you calculate the right pseudo inverse. So depending on the kind of problem that you have to take either the left pseudo inverse or right pseudo inverse. But if you have computational softwares like MATLAB or Mathematica, there are inbuilt commands to take pseudo inverse. You don't really have to specify left pseudo inverse or right pseudo inverse. You can simply specify pseudo inverse and it will appropriately take the right action. So we'll move on to some sample problems. So this will probably help you to solve the tutorial questions, because this will be more or less similar. You can expect more or less similar questions for your quizzes, weekly quizzes. So if any of you have any doubts regarding this session, you can always ask. You can interrupt me. You can. I would suggest you to use your microphone, because if you type anything in the chat box, it's very easy for me to miss. So if you have any questions until the topics that we have discussed so far, or if you have any doubts as we discuss the questions, feel free to let me know. Okay, so if you also feel to answer these questions yourself, you can also do that. So I'll give you a few seconds. If you feel like you can answer this, you can answer also, right? So that'll be a good exercise for you also. So question one would be, if the number of controllable degree of freedom is equal to the total degree of freedom, then such systems are called mobile robot, holonomic robot, non-holonomic system, differential drive, structure manipulator. So which option is correct? If the number of controllable degree of freedom is equal to the total degree of freedom. So like if you have a mobile robot and you can control a mobile robot along U, V, and R in all possible directions, right? And the total degree of freedom of mobile robotic system that it can have is 3, because it has 2 translation and 1 rotation. And if all the degree of freedom can be controlled, then the systems can be called as, it's a
Holonomic.
holonomic robot actually, right?
Yeah.
Yeah. So yeah, if you cannot do that, like for example, if you have a differential robot like this, right? So if this is x-axis and this is y-axis, the differential robot cannot move here, no matter what combination of angular velocities you give, it cannot move this direction, right? So that makes it not holonomic. But if the controllable degree of freedom is equal to the total degree of freedom, then such systems are called holonomic system. So I hope that is clear. If you check the solution, the answer is holonomic system. So I hope that is clear. So moving on to question 2. So if there are less number of equations than the unknowns, then the system is underspecified. Is it true or false? Less equations than unknown. So like if we have U, V, R over here, this is a 3 cross 1 vector. You have a W matrix over here, and you have omega 1, omega 2, omega 3, omega 4. So this will be 3 cross 4. So number of unknowns here is actually more than the number of equations. So yeah, I've got an answer to be true. One of you have responded, GP has responded it to be true. So like, I suppose we don't need any further clarifications to this. It's indeed true. Okay, so this is a numerical problem. So you have a matrix over here, which is A is given as 0 0.1, 0 0.1. The next column, next row would be 0, 0, then 0 0.5 minus 0 0.5. Then what will be the pseudo inverse? So here, what inverse would you be taking? Would it be the right pseudo inverse or the left pseudo inverse? Is it left inverse or right inverse? So here, if you check the order of this matrix, this is 3 cross 2, right? So that means if you have zeta as W times W, if W is 3 cross 2, then omega could be only 2 cross 1 and zeta could be 3 cross 1. So what does this mean? This is basically an overspecified system, right? Because it has more equations than the unknowns. So like we have just seen what inverse we should take in terms of an overspecified system. Yes, overspec system. So if that is the case, we have to take the left pseudo inverse, right? That is nothing but W transpose W, the whole inverse W. This will be your left pseudo inverse. right? So if you do this math, what will the answer be? I think the answer should be option A, right? Or if you have MATLAB or any other software, MATLAB or Octave, you simply have to put pi in v. This is the function that you would use, pi in v a. If you do this, you will get the pseudo inverse as 501 and 50 minus 1. Or you can do this manually. If you have a calculator, you can actually do this operation. So W transpose W would be a square matrix. So you have to find the inverse of the square matrix and multiply with the matrix.
Sir, here W and A, are they both the same?
Yeah, it's both the same actually. I've simply changed the notation.
Okay, okay, fine.
Is there a mistake here? I think this is W transpose, I think, right? I think this should be W transpose. Yes. So you can check it yourself. If you do this operation, W transpose W, the whole inverse, W transpose. If you do that operation, you would get the correct pseudo inverse, that is the left pseudo inverse for the system. So the answer is indeed option A, right? I hope that is clear. If I need to clarify it any further, I can do that, but you have to let me know. Okay, so option 4, this is a lengthy read. I'll read it line by line. So it says for a robotic system with more controllable inputs than the system states, right? That is the statement. For a given system state, multiple control output can be possible, right? The second statement says the control input with minimal norm is obtained by minimizing the objective function. This one, f is the square of omega plus lambda transpose theta minus w omega. And the exact solution for the above optimization problem is this one. So select the correct statements. So which of the options are correct? Is it is only statement 1 is true, or is only the statement second is correct, or whether multiple statements are correct or not? So like we'll go one by one. So it says the system has more controllable inputs than the system states. So I'll give you an example. Zeta would be W times W. So if the system has more controllable inputs, so for example, if zeta is always going to be 3 cross 1 because zeta is U, V, and R. And if the number of controllable inputs omega is greater than zeta, so for example, omega could be omega 1, omega 2, omega 3, omega 4. So this could be 4 cross 1, this could be 3 cross 1, and W would be 3 cross 4. Right? So this is kind of a wide matrix. It is a wide matrix, fewer number of rows than the number of columns. So we basically know what kind of system that we are dealing with. This is what kind of system is this? Is this an underspecified system or an overspecified system? Can anyone answer? Because from the statement itself, it should be apparent that it should be either underdetermined or overdetermined system. So what is that? Okay. Like, is it not clear, or you guys simply prefer not to answer? Okay, so anyway, like if the number of unknowns is more than the number of equations, so it's obviously an underspecified system, right? So we are dealing with an underspecified system. So for an underspecified system, just like what we have done, it can have multiple solutions. So out of the multiple solutions, we prefer to take the solution that has the least norm or the minimal norm. And we find the solution for minimal norm by minimizing this objective function over here, right? Minimize norm subjected to the constraints. So this is what our primary objective is. Minimize the norm subjected to these constraints. We have to find omega such that it satisfies these constraints, and also it will also have the norm as minimal. Right, so that is true. This statement 2 is actually true because we are dealing with underspecified system, and to find out the minimal norm, we use this objective function, right? The control input with minimal norm is obtained by minimizing the objective function, this one. So statement 2 is obviously true. Then what else can we say about underspecified system, right? Yeah, so statement 1 is also correct, right? For a given system states, multiple control inputs can be possible. Like for if you have a desired UVR, if this is actually a desired parameter, you want the system to achieve a desired UVR, there could be multiple combinations or multiple vectors W1, W2, W3, W4 that can be realizable, but out of which we prefer to go with the vector that gives you the least norm, right? So both of them are equal. Both of them are actually true. Statement 1 and 2 are actually true. Like for a given system state, multiple control inputs can be possible, and the control input which the minimal norm is obtained by minimizing the objective function so and so. And what does the third statement say? It says the exact solution for the above optimization problem is omega is W transpose W, the whole inverse W transpose zeta. So is this true or not? So what inverse is this? And what pseudo inverse should we take for an underspecified system? So what I have written here is a left pseudo inverse. And for underspecified system, just as we have seen in the previous slides, it should be right pseudo inverse. But this basically denotes left pseudo inverse, but we want right pseudo inverse. So in that regard, this statement is false. Okay, so out
Sir,
of all, yes,
even if it is a right pseudo inverse also, but
yeah,
the word exact may not be right because you're telling some norm has to be made.
yes,
So it will be a
yes.
just solution. It will not be an exact solution, even if it is a right pseudo inverse. Okay.
It's still an exact solution, right? It's still an exact solution because you can still satisfy this condition zeta minus w times omega. You can fully satisfy, or you can basically fully satisfy this constraint. So, like
Mhm.
as long as you can satisfy this, it's an exact.
Okay. Okay, sir.
But yeah, but in the earlier case, but when the system is overdetermined, whatever you find out using whatever you find out using the left pseudo inverse, you cannot satisfy this equation. You are
Okay.
only minimizing the error actually. So there will be a small error, but the solution that you are picking would be having the least error actually. But there is always going to be a difference between LHS and RHS. But here there won't be any difference. So that is why I called it as an exact solution.
Okay. Okay, sir. Thanks, sir.
Okay. Yeah. So in this regard, the correct option would be options 1 and 2. So I think option 4 is correct. So I hope that is clear. Yes, statements 1 and 2 are clear. Okay, so question 5. I think this is a different question. Yeah, so we'll look into this. For a robotic system with more system states than controllable inputs, right? So again, we'll write this as zeta as W times omega, and zeta would be again UVR this will be a 3x1 vector. And the question says that the controllable inputs is lesser than the system states, or system states is more than the controllable input. So omega 1, omega 2, it's made purposefully lesser, so it could be 2x1. So W would be 3x2. It's basically a tall matrix. So again, this is nothing but an overspecified system. Overspecified. Right? Then what else? What exactly what can be recalled regarding overspecified system? Because we cannot actually find an exact solution. We can only find an approximate solution that minimizes the norm, minimizes the error between the vector zeta, the left-hand side, and the right-hand side, W times omega. And the approximate solution would be omega star would be, you have to take the left pseudo inverse, W transpose W inverse W transpose zeta. So this is the approximate solution. And this term is the left pseudo inverse. So like with this in mind, shall we go through each of the statements? So statement 1 says an exact solution for the controllable inputs for a given vector of system states can be obtained as W inverse zeta. Okay, so it has multiple problems. It says an exact solution. So we know we cannot have an exact solution. We can only have an approximate solution. And it also says we can simply take a regular inverse rather than a pseudo inverse. Right? So you cannot obviously take an inverse just like this as you would take in case of a square matrix. So that itself is false. So you cannot do that. You have to take a pseudo inverse, not because non-square matrices are not invertible as a square matrix. So that is false. Yeah, so moving on to statement 2, it says an approximate solution can be obtained by finding omega star such that it minimizes the least square error zeta minus W omega. So that is true. That is exactly what we have just said. So statement 2 is correct. And what does statement 3 say? Statement 3 says the analytical solution to the above least squares problem is W star is W transpose W transpose the whole inverse zeta. Okay, so we also know for a fact that that is false because this is the right pseudo inverse. Whereas, in fact, what we want here is the left pseudo inverse. This is the left pseudo inverse. Right? For an overspecified system, we consider the left pseudo inverse. But here, the statement says we should consider the right pseudo inverse. Right? And the easiest thing is that the inverse is actually coming at the right extreme of this entire term. And here, the inverse is actually coming at the left extreme of this entire term. So that's also an easier way to remember which is right pseudo inverse or which is left pseudo inverse. Right? So in that regard, option statement 3 is also false. So the only correct statement is statement 2. So in that regard, the correct answer is option B. Okay, so I hope that is clear enough. Yes, statement 2 is the correct option. Okay, so another question on similar lines. So it says for a given land-based mobile robot, the wheel configuration matrix is given as W and M is greater than N. So W is a wheel configuration matrix of the order M cross N. And if M is greater than N, we have seen that in the previous slides that this is going to be an overspecified system. Right? Okay, then we'll go on with the remainder of the question. Then what will be the pseudo inverse W plus? At what condition does the pseudo inverse exist? So when will you get an identity matrix? So we have three questions, right? So each of the questions basically consists of an expression for a pseudo inverse, and it also asks for the condition at which the pseudo inverse exists, and when will you get an identity matrix. So like if you have a square matrix, you know that W, if W was a square matrix, W inverse or W inverse W, both will give you an identity matrix. But in case of a left pseudo inverse, if you take a left pseudo inverse of W plus W only will give you I if and only if W plus is left pseudo inverse, and W plus would give you an identity matrix only if W plus is right pseudo inverse. And these are not interchangeable. Right? And the rest of the statements are actually straightforward because we have seen that in the previous slides. So like for an overspecified system, we will take a left pseudo inverse, that is nothing but W transpose W, the whole inverse, W transpose. So which of the options basically corresponds to this entry? So I think, yeah, options 4 and 5 and 6. 4, 5, and 6 corresponds to left pseudo inverse. We can disregard all the first three options. And you also know that in order for the pseudo inverse to exist, there should be a regular inverse of W transpose W. This should exist. This should exist. And if this should exist, if W transpose W inverse should exist, then the determinant of W transpose W should not be 0, right? Because like for a square matrix, if A is a square matrix, A inverse will only exist if determinant of A is non-zero, right? So similar reasoning, W transpose W is a square matrix. Its inverse will only exist if determinant of W transpose W is non-zero. So which of the options corresponds to that? So W transpose W is not 0. So I think options 4 and 6 corresponds to that. So we can disregard option 5. And left pseudo inverse will only exist for the identity matrix can only exist if you pre-multiply the left pseudo inverse with the matrix itself. Not if you post multiply. It will only exist if you pre-multiply. So in that regard, option 4 is the correct answer.
Was that for the more specified system, or will
Yes.
it be same for the W plus
No.
W?
For underspecified system, you have to post multiply. See if you're taking the right pseudo inverse, you have to post multiply.
Okay, sir. Okay.
Right pseudo inverse, the inverse comes at the right. Left pseudo inverse, the inverse comes at the left. Right? Okay, so that case, the correct answer is option 4. For question number 6. Yes, so this is the correct answer. So moving on to question 7. So we'll solve a few numericals. So yeah, in a two fixed differential drive mobile robot, so I'll briefly depict the sketch of a differential drive robot. So this is the chassis of the robot. You also have a body frame attached over here, XB, YB. You also have two wheels independently powered using two motors. So as per our convention, we'll call this wheel as wheel 1 and this wheel to be wheel 2. So what are the data that have been given in the question? So it says the left side wheel angular velocity is 2 radians per second. So as per our convention, the left side of the wheel, left side of this chassis, if this is the chassis, and if this is the x-axis, this will be the left-hand side wheel, and this will be the right-hand side wheel. So, and that is also our omega 1. Left-hand side wheel is also our omega 1. So, omega 1 is given as 2 radians per second. And omega 2 is given as, here it is the right-hand side. Wheel angular velocity is given as 4 radians per second. That is 4 radians per second. And it also says both wheels are the same size and the wheel radius is 10 centimeters. So as per our convention, A is 10 centimeters. So if I convert that into meters, it will be 0.1 meters. So it's asking what will be the longitudinal velocity u. That is our question. So what will be the longitudinal velocity? So you can solve this using this wheel configuration matrix. You know this relation, zeta as W times omega. And in this case, what were zeta and omega? If you can recall, the wheel configuration matrix for our differential drive is UVR. This will be A by 2, K by 2, 0, 0, minus A by 2D, A by 2D times omega 1, omega 2. So if this is the case, I can also take this A by 2 as outside, A by 2 as outside. So you will end up with 1, 1, 0, 0, minus 1 by D, 1 by D. And if you multiply this with the given angular velocity 2 and 4, so if you multiply this out, what will you get? It will be A by 2 times 2 plus 4, that is 6, right? 6, then the second would be 0, and the third entry would be minus 2 by D plus 4 by D. This will be your UVR vector. And the question specifically says you have to find out the U, the component U. So here the component U would be nothing but 6A by 2. So that will be 6 times what is A? Here A is wheel radius, that is given as 0.1 and divided by 2. So that will be 0.3. 0.3 meters per second. I hope that is clear.
Yes, sir.
Yes, okay. 0.3. Or you can also take this average of both of these in order for you to get in order for you to get the wheel velocity, because if you consider this to be the midpoint of the chassis, the left hand side will have a velocity that will be how much? That will be r omega, right? That will be 2 times 0.1. This will be 0.4. And the right hand side wheel will have 4 times 0.1, right? 4 times 0.1. Sorry, this will be 0.2. This will be 0.4. Right? Sorry. if you draw a vector diagram, something like this, yeah, this is the middle point, and this is the left side, and this is the right side. This will be 2 times 0.1, and this at this extreme end, this will be 4 times 0.1. This will be 0.4. This will be 0.2. So at the middle point, like since this is a linear line, since this is a straight line, the middle point will have a velocity that is 0.3. So in that way also you can easily solve. It's nothing but the average of the linear velocities of the extreme ends. So yeah, the correct answer is indeed 0.3. If you cannot recall, because for all the other problems, you will be given the wheel configuration matrix, but in case of a differential drive, you probably won't be given uh, the wheel configuration matrix. Sometimes it may be given, sometimes it may not be given. If it is not given, you can, if you can recall this, you can easily recall it. Or otherwise, you can simply, write down the angular velocities of either ends, sorry, the linear velocities of both of these ends, and you can easily interpolate so that the velocity at the middle point would correspond to the linear velocity of the robot chassis, that is u. And whatever be the case, you all know that uh, the lateral velocity is always going to be zero, because for a differential robot, it cannot have a lateral velocity component. That is always going to be zero. So in that case, the correct answer is indeed 0.3. Okay, so we'll move on to question 8. So it's regarding mechanism wheel drive. It says, yes, for a mobile robot with 4 mechanism wheels, the wheel configuration matrix is given as so and so. So like if the robot is to purely rotate about its own axis in the clockwise sense, then what will be the right combination of the angular velocities? So you should also consider the length L greater than the depth. So again, simply for representation, I'll recall, or I'll try to take a screenshot. 1 second, be more convenient. Okay, copy. I guess we are on question 8. Yes. So this is the mechanism wheel drive that we are talking about. I'll keep it. Where shall I keep it? I'll keep it here. So we have to find out the combination that will make the mobile robot to purely rotate about its own axis in the clockwise sense. So that means it has to rotate about this point in the clockwise sense. Pure rotation. So how will you solve that? So we also know that zeta is W times omega. And if the robot is purely rotating, then how will zeta look like? Zeta will look like, because since it is pure rotation, it'll be 0, 0. And since it is rotating clockwise, you will have a negative term, negative constant, maybe k. This is how your zeta vector would look like. And you have to select the right combination of omegas, omega 1, omega 2, omega 3, omega 4, such that W times omega will give you something similar to this. So out of these options, which will give you this option. So I'll simply write this omega vector, W matrix here. I'll simply reproduce that. 1, 1, 1, 1, 1, minus 1, 1, minus 1. So minus 1 by d minus L minus 1 by d minus L, 1 by d minus L, 1 by d minus L. So like what are these options actually? It says the first option says omega 1, omega 2, omega 3, omega 4 as omega, 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 omega. So like
That
if all four wheels are moving in the same direction with same magnitude, what will happen? So obviously it will go forward, right? And the second option says omega minus omega minus omega minus omega minus omega.
it will go
So
backward.
it will go backward. Then the third option says the first wheel is omega, second wheel is minus omega, third wheel is omega, fourth wheel is minus omega. So this is omega, this is minus omega, this is omega, this is minus omega. That is one option. Then we have, this option, option 4. So omega 1 and omega 2 are minus omega. So it will go this way, it will go this way. Omega 3 and omega 4 goes in this direction. So like if you use some logic, how should it look like? Because if these two wheels are rotating in one direction and if these two wheels are rotating in the opposite direction, then it will probably try to induce the robot to rotate in this sense, right? If both of them are going in this direction, and on the other side, if both of them are coming in this direction, right, it may try to rotate the mobile robot clockwise, right? Or if these two wheels are going in this direction and these two wheels are going in this direction, it may try to induce the mobile robot to rotate counterclockwise, right? This is how the vector looks like. So we'll go one thing. We'll go with the easiest option. If omega 1 and omega 2 are going along this direction, for example, this is omega, this is omega, and if this is minus omega, minus omega, see whether it will give you the right solution. So omega, omega, minus omega, minus omega. So if you multiply this out, what will you get? So the first row would be omega plus omega, it'll be 0, right? Second row would be omega minus omega minus omega plus omega, that is 0. Yes. And the third option would be, how would it look like?
minus 4 by d minus L.
Sorry, what will that be?
Minus 4 by d minus L.
Minus 4 by
D minus L.
d minus L. So yeah, this is more or less similar to this, right? First two entries are 0. But what about the third entry? Right? It also has a negative here. We also wanted a negative here. But is this term really negative? We are also asked to consider L to be greater than D. Right? If L is greater than D and if D is less than L, then the numerator will also be negative, right? So in effect, this term would be positive. This entire term would be positive. Yeah. I think you got it. D minus L could be negative. So this negative and this negative would get cancelled. So that becomes positive. So if that is the case, then the mobile robot would rotate in counterclockwise direction, but we want it to rotate along clockwise direction. So in that case, what happens if you invert this? If it is if it is minus omega, plus omega, and plus omega, first two rows are always going to be 0. And the third option would be, how will the third, it'll be plus 4 d by L, right? And since d is less than L, this term is always going to be negative. So that is what we get here. We want a negative term here as the third entry. We will get a negative entry here if this is the combination. So the correct answer would be minus omega, plus omega, plus omega. That will be the correct answer.
But when we look at by drawing arrows, It was
Yeah.
showing anti-clockwise, right?
Yes, by showing arrows, it may try to rotate to it may feel like it will rotate in anti-clockwise, but in reality, that is not the
Anti-clockwise.
case.
Okay, okay.
It'll rotate clockwise. So like if you have another configuration, like instead of this configuration, if you have a mechanical drive with these configurations, actually see, I hope you can see what I'm doing. The direction of the wheels are actually flipped. Now this may give more intuitive rotations actually. So compared to this, the rollers direction are actually flipped,
Okay.
right? So if you go with this configuration, then it may rotate in the exact same way as how we drew this arrows,
Okay.
right? And this configuration matrix is exclusively for this mechanical. But if you are flipping the rollers, if you are flipping the roller axes and all those things, we may get a different W matrix, and that may lead to something else. Okay, so the correct answer in this case would be minus omega plus omega plus omega. I think it is option 4. Yes. And this is also similar problems. But since we are okay, I'll anyway solve this problem because this could be a good question. So here it says for a mobile robot with 4 mecanum wheels, right? The wheel configuration matrix, just like in the previous case, is given as so and so. W is so and so. So if the mobile robot is to move diagonally in the first quadrant, keeping the initial orientation, then what will be the right combination of the wheel angular velocities? So again, if I reproduce the mechanical wheel over here, and we want the mobile robot to move like this diagonally in along the first quadrant, right? And by keeping the same orientation. So like at at the initial position, it will be like this. At a later configuration, it will be like this, like this, like this. Right? It won't rotate. It will go diagonally. So if that is the desired motion, then what is the correct combination of? What should be the right combination of the wheel velocities? So again, I'll reproduce this. Theta is W times omega. And if the robot wants to go in diagonal position, how would zeta look like? So we already know that there won't be any rotation. So the R component would be 0. And U and V component would be identical because they are moving with the same velocity, that too along the diagonal. So both of them should have exactly same magnitude and same direction, right? So if I reproduce the W vector, this should be A by 4 times 1, 1, 1, 1, 1 minus 1, 1 minus 1, minus 1 by B minus L, minus 1 by D minus L, 1 by D minus L, 1 by D minus L. So what combination of omega will give you KK0? Right. So one option is you could try each of these options one by one. So omega 1 is 0. So like it's first option said this is omega 1, this is 0, this is 0, this is omega. So you're only powering the front wheels. So that does not look too likely. What about option 2? Option 2 says this is minus omega, this is 0, this is 0, this is minus omega. Again, you are only powering the front wheels. That also does not seem very likely. So what about option 3? Omega 1 is omega, omega 2 is 0, omega 3 is omega, omega 4 is 0. So you are actuating the diagonal wheels like this. And you are not rotating second and fourth wheels. So that seems pretty, intriguing. We'll try with that option. First, we'll try with that option. So omega 0, omega 0. So if you multiply this out, you will have an a by 4 outside. So this will be omega 0, omega 0. So there will be 2 omega, right? The first entry would be 2 omega. The second entry would be omega 0, omega 0. That will also be 2 omega. The third entry would be this is minus, this is 0, this is plus, this is 0. This is also 0, I guess, right? So this is how our zeta vector would look like, right? So 2 omega, 2 omega 0. So the first two entries have constant identical magnitude and the third entry is 0. And this is exactly how we desire our zeta matrix would look like so that the robot can move diagonally. Right? So in that case, I think we can all agree that option, what was that option? Option 3, I guess. Option 3 is correct. Right? Yes. Option 3 is indeed correct. So I think we have a few more questions. I think we have 4 more questions actually. So we'll try to wind it up quickly. So this is now corresponding to omni-wheel robot, right? So yeah, we only have a few more questions. So I'll again reproduce the omni-wheel robot for your reference. I'll take a screenshot, copy. So for question 10, we have an omni-wheel drive. So it says for a mobile robot with 3 omni wheels, the wheel configuration matrix is given as so and so. So if the robot were to move along positive longitudinal direction along x-axis, this is the x-axis of the robot, then what is the right combination of the wheel angular velocities, right? So again, zeta should be w times omega. And since the robot is moving along the longitudinal direction, zeta should look like a positive constant k, then all the other entries should be 0 because it's only going along the longitudinal direction. It should not go along lateral direction or nor it should rotate. So what should be the correct combination of omega so that we'll get this a vector similar to this form. So if I reproduce w, this should be 0 minus a root 3 by 3, a root 3 by 3, 2a by 3 minus a by 3 minus a by 3 by 3l, a by 3l, a by 3l. Then what should be omega? So like intuitively, if you want to go forward, like if you try to have any angular velocities here, it may have a tendency to rotate and it also has a tendency to go along y-axis if you actuate this wheel. And if you rotate these two wheels, what is going to happen? These two wheels, if you resolve it, it can have two components, but these two components will cancel out. It can only have a resultant component along this direction, right? If you have a velocity like this, if you have a velocity like this, if you resolve everything along x and y direction, these two will get cancelled. Only the component along x-axis can remain. So like obviously we can basically select an option with omega 1 as 0. So we can either go with option 5 or option 6. We'll go with option 5 first. So if 0 minus omega omega, if we go with this option, how will it look like? So if I multiply this out, this will be, if the first element would be 0, this is 0, this is plus something, this is minus, sorry, this is plus something, this is plus something, right? Both are plus. So we'll get 2 times a root 3 by 3 And if we go by the second row, this is 0, this is plus, this is minus. So that is 0. And third entry would be this is 0, this is minus, this is plus. So that is also 0. So again, it is similar to what we have obtained earlier, something similar to a constant, then all the other entries should be 0. That is exactly what we got here. The constant plus all the other entries are 0. So if that is the case, this is the correct configuration, 0 minus omega, omega. So option 5 is indeed correct. If we choose the other option, if we flip the velocities of the second and third wheel, instead of going in this direction, the robot will go in this direction. So option for question 10, option E, the second last option is indeed correct. Yes, and one more question regarding the omni wheel robot. So I'll just again reproduce it. The question is still the same, but the only change is now we have to make the robot move along the positive y-axis. So if the robot has to move along positive y-axis, zeta, which is w times omega, zeta should look like 0, a positive constant along v-axis, then no component along r, no r component. So again, how should the w matrix, how should it look like? So again, I'll try to reproduce this field matrix, copy. If I paste it over here, okay, it's okay. If I paste it over here, then what should be the combination of omegas? So if it has to move along y-axis, can anyone suggest? Because the first option says omega, omega, omega. So if all the wheels are rotating with equal magnitude and equal direction, this will have a tendency to rotate in clockwise direction. And if all the wheels are rotating with the same magnitude but in opposite direction, then it will have a tendency to rotate in the clockwise direction. And what about this option? Omega 1 is omega, omega 2 is minus omega by 2, omega 3 is minus omega by 2. We'll try with that. Omega minus omega by 2 minus omega by 2. If you multiply this out, the first term would be 0, right? Because these terms are identical, these terms are identical. This is a positive term, this is a negative term. And if you multiply the second rows, this is, yeah, what will that be? 2, yeah, that will be 2 by 3 minus 1 by 6. Sorry, 2 by 3 plus 1 by 6, right? If I'm not mistaken, plus 1 by 6. So 2 by 3 plus 2 by 6. This will be, yeah, this will be a positive constant actually. And the third entry would be, yeah, a by 3l minus a by 3l minus a by 3l. Yes. So these are identical. And this is 1, this is half, this is half. So 1 minus half, that is also 0. Yes. So yeah, we'll get the right vector with this combination, I suppose. unless I'm not very much mistaken. So the correct vector would be omega minus omega by 2 minus omega by 2. I hope you all agree with that option, right? If you multiply this with this, we'll get a vector similar to this 0, k, 0, because that is precisely what we want in order for the robot to move along the positive direction. I didn't get the question actually. Lateral direction is first quadrant like the previous sum. Could you clarify that? Because I didn't get that. I didn't quite get your question. Can you speak up, GP? Okay, like as far as the question asks, we want to find out the
So, what I
yes,
meant, just like the diagonal movement of the omni mechanism in the previous sum,
yeah.
uh, in this sum, the positive y-axis will mean the first quadrant, right? The movement will be similar to the diagonal movement of the omni in the previous sum.
No, no, no. The diagonal means the robot will move like this.
Correct, correct.
Equal
But
velocities along x and y direction. But here it will only move a lateral direction along y-axis, strictly along
okay,
y-axis,
okay, got it.
right? So this is the first instance. At the second instance, it will be here. At the third instance, it will be here, right? Pure
Understood,
strictly along y-axis. So that is why it
understood,
says lateral direction along positive y-axis. Okay. So
understood.
that is okay. Thank you. So that is indeed the correct answer. Option C. Yes. So we'll go with the second last question. So it's an inverse problem what we have solved earlier. So for mobile robot with 3 omni wheels, the wheel configuration matrix is given as so and so. If the wheel angular velocities are as given as so and so, then how will the robot move? How will you tackle this problem? Again, we have this relation zeta as W times omega. We have W over here. We have all the omegas over here. So what should we do? We'll simply multiply it out, right? 0 minus a root 3 by 3, a root 3 by 3, then 2a by 3, minus a by 3, minus a by 3, a by 3l, a by 3l, a by 3l. If you multiply this with this omega vector, this is omega. Second entry would be minus 3 omega by 2 minus omega by 2. Third entry would be root 3 omega by 2 minus omega by 2. So if you multiply this out, you will get the zeta vector. And based on the zeta vector, you can determine how the robot moves. So can anyone help me solving this equation? So the first entry would be 0. It'll be plus a times 3 omega by 6 uh, a plus a root 3 omega by 6. I hope I'm correct. A times 3 omega by 6, then plus a root 3 omega by 6, right? Then the second entry would look like 2 a omega by 6. Then second entry would be plus a root 3 omega by 6 plus a omega by 6. Is this correct? 2 omega by 6 a root 3 omega by 6. Then we have this term, a omega by 6. Then this term plus, sorry, we have minus a root 3 omega by 6 plus a omega by 6. Okay, this entirety is the second row.
Will be 6L, sir. The last row will be, denominator will be 6L.
Last row.
Denominator minus a root 3 W by 6L. 6L. It's 3L, I think, everywhere.
Yeah. Here at the last row, actually.
Yeah. A by 3L.
Okay, so we haven't gotten to the last row. So the first entry would be a omega by 3L, right?
A omega by, yeah.
No, the last row. No, this is basically
No.
the first row. This is the second row.
Yeah, first row would be a omega by root 3, no, sir?
First row, a omega by root 3. Are you talking about this one?
Yes, sir.
Total.
Because, W1 is W
Yes.
omega, and
Yes.
you have 0 and a omega by. Yeah, okay. Correction.
Okay. So the final entry would be a omega by 3L plus minus a root 3 omega by 6L, then minus a omega by 6L, then a root 3 omega by 6L minus a omega by 6L. It's all very tricky, I guess. Okay, so if everything pans out, how will each of these terms would look like? This is first term would be 3a omega by 6 plus root 3a omega by 6. The second term, if you simplify, I think these two terms will get cancelled. So the second term would be, again, if you have, you can sum these terms. 2 omega, it's also a 3a omega by 6. Plus you also have this a omega by 6, I think. A omega by 6. And the final row, this is the first, this is the second, and this is the third row, would look something like a omega by 3L, a omega by 6L. Yes, so I think these two terms will get cancelled because these two terms are minus a omega by 3L, that will get cancelled with this one. So these will get cancelled and these will also get cancelled. So the third row is basically 0, right? So how will this move? Like we have a positive, zeta will look something like a positive quantity here, K1, K2, and the third entry would be 0.
Even the first row will become 0, sir, because you left out the negative sign minus a root
Yes.
3 into W. And
So
then
you say the first row is going to be 0. Is that so?
Because W into 0 plus W into minus a root 3 by 3 plus W into a root 3 by 3.
Yeah, like the problem is I think we have made a mess out of this. So we'll do one thing. We'll create a fresh page and see it more neatly. I think that is.
Sir, would you mind if I make a request?
Yeah, sorry.
Sir, showing how the matrix looks like is
Yeah.
sufficient. That doing that calculation, you may leave
Uh-huh.
it to so that we go home, or if you want to do it, put it in your MATLAB and just say A equal to
Okay,
BW.
okay, okay. I'll do one thing. I'll do this in MATLAB. Okay, I can share my screen actually, right? That would that be enough?
Yeah, because after giving a talk of 2.5 hour session, having that kind of focus is very, very difficult.
Yeah. That's what I'm struggling actually. I'm losing my focus. So I'll do one thing. I'll stop mirroring. I hope you can see my screen. One second.
In future also show only the matrix how it looks like and
Yeah.
give whatever your interpretation
Sure.
comes for calculation, switch it to
Yes.
MATLAB.
So yes, I'll thank you for your consideration. I'll take that definitely into consideration. So like I'm struggling here actually. So yeah. So I'll define some variables. Sims is a command to define variables. So our only variables are a and l, right? So I'll write our W matrix to be 0 minus a times square root. Okay, square root 3 by 3. Then this third entry would be a times square root 3 divided by 3. The second term would be 2 times a by 3, then minus a by 3 minus a by 3, right? The final entry would be a by PL, sorry, a by 3 times L. I'll just copy this one. So I hope this is our correct, sorry, W matrix. No. Where have I gone wrong? Okay. This is where I have gone wrong. Yes. So this is our W matrix actually. 0 minus a root 3 by 3, a root 3 by 3, 2a by 3, minus a by 3, minus a by 3, a by 3, a by 3, a by 3. So we also need to define our W's. So I'll define omega as W. Okay, then W1 would be W. W2 would be minus square root of 3 times omega by 2 minus omega by 2, right? Then omega 3 would be the same thing, I suppose. Minus square root 3 times into omega by 2 minus omega by 2 plus, but here I think this is the positive. Okay. So now if you multiply W with this vector W1, W2, W3, and if I simplify this answer, yes, can you see that? It is A omega 0. Is it clear? Is that seen? Okay, so I'm switching back to my slides. I hope that is clear enough.
So the first term also has to come out as 0. It's a simple.
No, it does not have.
The W yes. has got 0 and a positive term and a negative term of equal magnitude. So when we do cross multiplication with omega, you have to get 0 when you add up the first term.
But I agree with that. But it has a negative term and a positive term. The negative term multiplies with a negative term. Right? No, negative term multiplies with a negative term. Positive terms multiply with positive term. So in effect, the net is actually positive.
So the W1 is only W, correct, sir?
Yes.
Omega.
Yes.
So when you multiply it with 0, add it up with a positive term and add it up with a similar negative term, the sum will be 0.
I cannot see how that is actually. So I'll do one thing. I'll simply solve that first equation alone. Fine. Right? That first entry alone. we'll take that alone into consideration because that is where we have that conflict. So yeah, just the first term. So yeah, 0 minus a by root 3, a root 3 by 3. In fact, I'll write this entire vector 2a by 3 minus a by 3 minus a by 3, a by 3l, a by 3l, a by 3l. Okay, so the first entry is omega, right? Omega. Then the second entry is what? What is the second entry? Minus root 3 omega by 2 minus omega by 2. The third entry is root 3 omega by 2 minus omega by 2. Okay, so just considering the first entry alone, so 0 multiplied by omega is 0 plus what do we have actually? This term multiplied by this term.
W. Okay.
Yeah, so that is minus a root 3 by 3 multiplied by minus root 3 omega by 2. Then it also has a second term, minus a root 3 by 3 multiplied by minus omega by 2. Then we have this term, that is plus a root 3 by 3 times root 3 omega by 2 plus a root 3 by 3 into minus omega by 2. So if you multiply everything out, this term I'll take it here, that is a root 3, that'll be a times 3 omega by 6, and this term would be plus a root 3 omega by 6. Then this term a times 3 omega by 6, then plus this term minus a root 3 omega by 6. So I think this term and this term will get cancelled. At the end, we'll get a times 3 omega into 2 by 6. So it becomes a omega.
Okay.
Okay.
Okay, sir. But maybe I made a mistake.
Okay. Thank you.
Thank you, sir.
It's okay. Yeah. So yeah, that's about it. If you multiply W times omega, you will get a omega 0. So if that is how your theta matrix would look like, how will the robot move? That was the question. So the first option says it will go forward along x-axis with gradual counterclockwise turning with finite turning radius. Is that correct? Because if you consider this to be the origin, what it describes is it'll go along x-axis, but it will gradually go in the counterclockwise direction like this. This is how the trajectory will look like. That is, but what do you think? How does this vector define the movement of the robot?
Diagonal movement.
It's exactly. It's diagonal movement. So if you have a mobile robot having two equal velocities along x and y component, will make it move diagonal. So if this is the first configuration, it will move here, it will move here, it will move here. That is how it should be moving. So I suppose we don't have to go through all the options. The correct option you yourself have found out. The motion will be diagonal actually. So the option says it will move diagonally along the fourth quadrant. Is it along the fourth quadrant or is it along the first quadrant? We have two options for diagonal. It's along first quadrant, right? Because all the velocities are positive.
Right.
Yeah, so it'll move diagonally along the first quadrant with equal linear velocities in both axes and keeping constant orientation. Yeah, so that's about it. I think, yeah, we also have, that is the correct solution. And yeah, we also have one more question. So I leave you to solve this. This is a straightforward problem again. So it says it's a four-wheel skid steering robot. You have the configuration matrix given as W, and you're also given the four-wheel velocities, omega 1, omega 2, omega 3, omega 4. Then the question asks, what is the instantaneous lateral velocity along the positive y-axis with respect to the inertial frame? You can consider at this instant, the x-axis of the body frame is oriented 90 degrees with respect to the x-axis of the inertial frame. So you have the inertial frame fixed at the ground. Let this be the inertial frame. This is xi, this is yi. And it is also given that at this instant, the robot is oriented 90 degrees with respect to the inertial frame. So if this is the robot's body frame, this will be xb, right? Because this is oriented 90 degrees with respect to the body frame. So as a result, yi would be along this, yb would be along this vector. And you have been given W matrix and the omega vector, right? So if you multiply omega times omega, if you multiply W times W, you will get this theta, right? Where this W is, as per the question, it is 4 omega, 3 omega, 2 omega, and omega, right? So if you multiply W times omega, you will get zeta. So once you get zeta, you have to transpose it back to the inertial frame of reference. How do you do that? So in the first lecture, first week, you might have come across the transformation between the inertial frame of reference and the body frame of reference. Use this transformation, eta dot as j of psi zeta. And where j is nothing but the rotation matrix, cos 90 minus sin 90, sin 90, cos 90, then 0, 0, right? So eta dot is what you want to find out, and specifically the y component of eta dot y, because that is what the question asks, right? It says the lateral velocity along the y-axis with respect to the inertial frame of reference. So what you have to do, you have to find out the value of phi, j of psi, multiplied by w multiplied by omega. You will get a 3 cross 1 vector and find out the y component, the second component, right? So if you want to do that, I can show that quickly. It's a by 4, or would you like to solve this as homework? A by 4, a by 4, a by 4. Then the second row would be 0, 0, 0, 0. Third row would be a by 4d, a by 4d, a by 4d, a by 4d. First two entries are negative. So you have 4 omega, 3 omega, 2 omega, omega. And if you multiply this through, what will you get? Yeah, it's again a lengthy process. So I would rather leave it to you, right? It's only a matter of solving this expression, j of theta times w times omega. Because if you solve only this much, you will only get theta. And if you pre-multiply theta with this Jacobian matrix, you will get everything with respect to the inertial frame of reference. So again, once you do that, I'll give you the answer. The correct answer is, I think, yeah, option B, 5a omega by 2. Right? So if you have any questions regarding any of this questions or any of the solutions that you have solved in this session, you can always reach me back to through the discussion forum. I'll be able to get back to you through there. Right?
Sir, kindly upload this recording into YouTube.
Yes. I'll upload this recording by today or at most by tomorrow. Before that,
last week's recording also kind of upload.
It was all it's already shared. Last week recording is already shared.
I have not seen an email. Okay, I'll go
Okay,
back.
it's shared. The slides as well as the recordings are all shared. The videos
Okay.
are also shared. This will be shared by today, or at most it won't go beyond tomorrow. I'll be sharing.
Okay. Okay. Thanks a lot.
Yeah. So with that, again, thank you all for joining. I don't think I have any more energy to continue any further. So yeah, with that, I am winding up the session. Right. So
Yeah.
thank you all for joining.
Thanks a lot, sir. You have really
Yeah,
put
thank
a
you.
lot of effort.
Thank you. Thank you.
Thank you for the patience.
Anything else?
That is all. Thank you.
Okay, thank you. Thank you. Okay, see you next week. Yes, thank you.
Okay.